My name is Sangmin, and I'm an assistant professor in the civil, environmental, and infrastructure engineering in the Southern Illinois University. I joined SIU in the 2021, and I'm teaching the water resources courses, such as the hydrology and hydraulics, and the fluid mechanics and water resources engineering. I got my PhD in the water resources engineering in the 2015 from the KAIST, Korea Advanced Institute of Science Technology. And after graduation, I worked at the University of Utah as postdoctoral researcher. And I still have studied the water cyber physical systems resilience and the sustainable, integrated water infrastructure management and the socio hydrology systems. So that is my research field.
Okay, great. So you're clearly an expert in the water infrastructure and engineering fields. So what are your thoughts on the world's water infrastructure? What are the most troubling aspects?
Water infrastructure in the world has been well operated in a centralized manner to supply and discharge water. And the many infrastructure systems in the many countries are facing the sustainability challenges from the climate change, population growth, and the cybersecurity and the energy security, food security. But the most challenge would be those disturbances are getting more uncertain and then their impacts are getting more extreme. So the water infrastructure has worked well, and then because they were well designed, considering the design criteria and then the conditions of design criteria at that time. But the conditions of the design criteria has been changing now. So everything is changing. The climate is changing and the population growth and then the demand is changing. The lifestyle is changing. But of course, the water systems have been expanded and extended considering the population growth. But the current water infrastructure system are not ready to provide the reliable water services under the extreme and uncertain, unexpected failure event. So I think this is the most the challenge in the world now. So for example, in the Texas winter storm, maybe power outage led to some water outage, water supply system problems. And then the California drought, and then recently the dam collapse and flooding in Libya. So those kind of things, the current water systems are not ready to cope with the extreme and unexpected the failure event. So this is, I think, the most challenge in the world now.
So you recently received a $200,000 engineering research initiation grant from the National Science Foundation. Can you describe what the grant is for and what problem you're trying to solve?
Basically, this project specifies the concept of the water microgrid and then try to develop the benchmark models of the water microgrid system and prove the microgrid the effect in the sustainability and the resilience. So water microgrid is a kind of a hybrid centralized and decentralized system. So for example, currently the centralized water supply system supplied water, and then we also could consider the local water sources for the water supply. So for example, the rainwater, the harvested rainwater, or treated the wastewater, or desalinated water, or groundwater. So the water microgrid, they incorporated those local water sources into the existing centralized water supply systems. So the water can be supplied from the centralized water system and the local water sources. And their portions in the water supply will be more decentralized and distributed. And the portions of their portions of the in the water supply will change depending on the energy efficiency or system efficiency or operational cost or the failure conditions. So this is why the water microgrid is kind of a hybrid, the centralized and decentralized system. But the configuration of the water microgrid is the network of the networks. So the current water distribution network can be further sectorized and then divided into the multiple subnetworks. And the subnetworks are interconnected through the centralized water system. For example, if there is, like the hub, if there is a big storage tank and the water the storage tank is filled with water that is supplied by the centralized water system. And then the water in the storage tank also can be supplied to the each subnetwork. So that's why I'm saying the subnetworks are interconnected through the centralized water system. And the subnetwork also has their own the local water sources. So the water is also supplied from the local water sources. So why this is really important is, and if there is a failure in a subnetwork, and the subnetwork can be isolated from the other subnetworks. So, the service losses from the failure event in a subnetwork can be further propagated to the other subnetwork, so that we can minimize the service losses from the failure event in terms of the overall system. And also the other interconnected subnetworks can help the minimizing the damage or losses in the water service in the disrupted subnetwork by the supplying the available water in the other subnetworks. So this is the actually this concept is well aligned with the resilience concept. The resilience means the minimizing the damage or losses from some failure event and the rapid recovery to the previous state. So this is the resilience concept. Also, the local water sources usually produced based on the water recycling or water reuse. So this means these options can be also the sustainability the options, like by the water recycling, the minimizing the environmental impact and the social economic impact. So that's why I'm considering the water microgrid that can achieve the system's resilience and the sustainability together. So this is the main concept. But there are so many challenges in practical implementation of the water microgrid, because we don't know how to configure and how to operate between the centralized system and the decentralized system. So this project basically addressed those challenges with the questions in the configurations and the operations of the water microgrid system.
All right, thanks. I want to talk more about your project in a little bit, but I want to make sure I understand the centralized versus the microgrid. So a centralized system, that like a city utility where all the the wastewater and goes into one and they clean it, and all of the clean water comes out from them. Are microgrids like just breaking that up so that there's several smaller parts of that system, or is it more like each building or even like a neighborhood or something contributes to the microgrid? How is it broken up?
So that is fundamentally the network of the networks. So the network means the centralized system already have the networks, and then the sub-networks will be incorporated into the existing water systems network. So yes, probably the local the water from the local water resources cannot be, I think, supplied for the drinking water purpose, I think, because the people don't want to drink the treated wastewater or the harvested rainwater. So my group's idea is to supply those water to the more public space, like a parking lot or the park or other irrigation in the agriculture area. So probably the local water sources and the treatment or facilities can be connected with the existing also the collecting system of the wastewater. So we are considering not the building scale, the water reuse. We are considering more regional scale of the water reused.
So to get a little bit more in the specifics of your project, how are you and your students building a lab scale physical model of a working microgrid system that can test various configurations and operations?
The lab scale water microgrid is actually the real world system of the water microgrid. So, but the scale is small and the size is a small scale and the lab scale. So we try to demonstrate real world the centralized water supply system first, and then we try to sectorize the lab scale the water distribution network with some like other water distributed water sources. So basically, the lab scale water microgrid will include the multiple the pumps to feed the water into the network and the multiple valves to isolate the sub-networks and control the flow, and the multiple demands and the multiple storage tanks to store the water, and then the water collected from the wastewater pipeline. And we also install the sensors for the pressure measurement and the flow measurement, because we need to analyze the hydraulic performance of the water microgrid. And so that would be some configuration of the lab-scaled the water microgrid.
So this is an actual a physical model. It's not just a computer model, computer generated.
Yeah, not the computer model. Of course, actually, while having some literature review about the power microgrid and the water microgrid or hybrid system, we realized that maybe we needed to more classify the water microgrid types, like branch types water microgrid or radial types of the water microgrid, considering the real world systems, because real world, the centralized water systems have a lot of different circumstances in the designing the water systems and different demand and different elevations. So considering that, we are actually now defining a lot of different types of the water microgrid models, and we are testing that through the hydraulic simulation model, and then we are going to build the one of the models we have tested. So the physical lab scale physical model is the physical model of the water microgrid, not the simulation models.
So how far along are you in this research project? And I'm wondering, how much are you utilizing your students? How involved are they in this project?
This project recently initiated, started on the July. So my student recently joined this project now. So far, we have just had the literature review about the water microgrid and power microgrid, because actually this concept is motivated by the energy microgrid, because the energy system has also similar problems like the water systems, like sustainability and resilience to the power outage or the carbon emissions. So they employed the renewable energy sources in the existing centralized power grid. So we are trying to understanding the principles and then the existing research result from the power microgrid the research. So the student have reviewed some lot of literature review, and as I mentioned, we are defining some various and different types of the water microgrid, and we will test them. We are actually testing the different types of the water microgrid using the simulation models now, and then we will build up the physical model of the water microgrid.
Okay, so as you get farther along, or even when you finish your project, how will your team share the results? Will that be through education and outreach activities? What will those look like, and are those part of the grant requirements?
Yeah, that is very important in my research, this project. For the disseminating this project outcomes, we plan to hold the water forums every year. So our department has the professional advisory board, and the members are the engineers and managers and agencies from the various different professional background in the transportation, the water supply and treatment, and the urban planning. So in the forum, we are going to discuss some gaps and the further improvement for the improvement in the concept of the water microgrid and its models. And we will also present the project outcomes in the conference. We already submitted the an abstract for the Environmental Water Resources Congress, the EWRI Conference 2024. And so we will present the first year project outcomes next year in the conference. And for the education, I'm going to incorporate those concepts, the water microgrid concept into my course. So for example, I'm going to improve the lecture slide by adding the concept of the water microgrid, and then adding the team project related to the water microgrid design. And another effort would be the outreach to the public and the K-12 student. So I have participated in the SIU World Workshop every year. And this workshop invites the high school student in the Southern Illinois area. And I have introduced the urban water cycle, and we had some time to design the competition for the water distribution network before. So now I can incorporate the water microgrid design into this workshop. And I also encourage the underrepresented student to be involved in this project. So 50% of my students are the female student, and then all the students are the international student. So all those activities were planned in my proposal, and then I would implement all those activities during my project years.
So that was part of the grant, is in your proposal, and so that all that education is that all sounds really great.
I believe this is a kind of an advanced type and model of the existing water distribution network systems. So because the teaching courses are usually address the water supply systems and the water distribution networks. So this is a really good model to introduce the advanced model for the water supply systems.
All right, that's great. I know you're relatively early on in the project, but has anything so far surprised you from this project, either from the results or just from doing the work with the students?
So because this is just the initiation stage, it's just the first quarter of the first year, project year. So so far I have not yet have some result or outcomes that surprise me. Yeah. But as I mentioned, we realized actually initially we planned to develop the best and optimal water microgrid model. But then now we realize that there is a need to classify the more different and various types of the water microgrid. And so we are defining some more various types of the water microgrid, like in the branch types or the radial types, considering the real world system application. So because our ultimate goal of this project would be application of this water microgrid into the real world systems. So considering the different circumstances in the water systems in the real world, so we try to make them various types of the water microgrid now.
So what advice can you give other engineers working on water infrastructure? What can they learn from microgrids and or decentralized systems?
The water systems are facing a lot of challenges from the lot of disturbances like climate and then socio-economic factors, and then also energy sectors and food sectors. I mean, those disturbances are getting more extreme and uncertain now. So, and as you know, the water sectors are interconnected with other sectors like transportation and energy and food. So the interdependencies, the interconnections between the water sectors and other sectors are also increasing now. So that means a failure in this water sector can be cascaded to the other sectors. Also, the failures in the other sectors can be cascaded to the water sectors. So understanding and evaluating those some system performance would be more complicated and complex now. So anyway, so I believe that considering the extremity and the uncertainty of the disturbances, I think there is an urgent need to upgrade the existing systems to cope with the extreme and uncertain disruptive event. So I would like to suggest like some more variety options, actually strategies. So I should explain this one actually now. So the water microgrid actually was motivated by the law of the requisite variety concept in the cybernetics field. So it means the variety can destroy the variety. So the second variety means the uncertainty of the circumstances or disturbances. And the first variety means some various options in the control on the management. So that means if the system can have more variety in the management options, they can address the uncertainty of the disturbances. So considering this, the water microgrid concept exactly follows this law of the requisite variety. So if we could understand about actually the cybernetics field, they proved this concept using the entropy equations. So if we could understand the entropy equations, the variety means the increase in the decentralization and the diversification. So water microgrid has some diversified water resources like dam water, rainwater, and the treated wastewater, and also those water resources are decentralized in the water supply. So the water microgrid actually implement this law of the requisite variety. So considering this, to cope with the extreme and uncertain disturbances, I would like to say there is a need to upgrade our systems with the more decentralized and diversified the manners. So water microgrid is just one of the examples to implement those diversification and decentralization. So we continue to discuss about what we can further diversify and decentralize our water systems to cope with the uncertainty and extreme disruptive event. So I would like to just suggest this one.
As all these systems are becoming more interrelated, as you're saying, what's the best way forward? Is it going to be through technology, like digital twins that kind of combine everything into a model, or is it more about communication and collaboration among different departments?
And analyzing some those interdependencies between across the water sectors and other interconnected sectors, yes, I believe in the simulation would be some separated simulation for each models, and then there is a need to make some framework to integrate individual simulation models for each sectors. And then more physically, I believe we can consider two strategies, two options to combine all those sectors. For the first one would be a smart system, like a cyber physical systems. So like using the advanced ICT, information and communication technologies, maybe through the information that we could combine and integrate those the water sectors and the transportation and other interconnected sectors. And the second one would be the community participation. So communities can be also like human sensors. And also they usually post their observations on the social media. So we can take some information from the social media. So maybe considering the interdependency, the water sectors and other interconnected sectors. So we could also increase the community participation in the managing those complicated interdependencies in the water systems and other sectors.